Hello, this is Jeffrey Fox here, and in this unit, we're describing the features that we use to classify the 51 big data use cases that is discussed in a separate section. These use cases are described there in terms of their algorithms and, more importantly, what they actually do, and some rather cryptic classification is given. These slides here flesh out that classification and give somewhat variable amount of detail depending on the classification. This work is based on that done by NIST, National Institute of Standards and Technology, who have a big data public working group which worked from June to September 2013. The leaders of that activity were Wo Chang of NIST, Robert Marcus of ET Strategies, and Chaitan Baru of UC San Diego. And of course, we remember, as always, in this class, which is also known not only as big data, but also as X-informatics, that the motto is to use clouds, running data analytics collaboratively, processing big data to solve problems in X-informatics. And here are all the various X-informatics that we have dug out over the last few months. In this lesson, we actually summarize that classification, and then we go in to give a little bit more detail of some of those classification areas. This was all done as part of the work of the requirements and use case subgroup of the overall big data public working group. So one of the things that we classify in those 51 cases is what's big, which is essentially what is the parallelism over. Big data runs on big clouds, which have lots of nodes and cores and processes and threads running simultaneously. That's parallel computing. The way you do parallel computing is to find some big number, which measures the size of something, and chop the things which is big up into parts and run one part on each thread or process, the so-called single program multiple data model. So if we look at those use cases, we found that the parallelism is sometimes over people, sometimes that's the users of an application, such as the users of a search engine, or it's the subjects of the application, like, I don't know, collecting census data, and sometimes both. There are a special class of users of application, like researchers or doctors. Like in the case of doctors, there are another set of users called patients. The doctors are the people who use decision tools to make decisions, and then they, in order to make a decision about one patient, they look at a lot of other patients, using parallelism over those other patients to speed up the analysis. A critical thing which there's parallelism over is items. Like many of the applications involve images, you have parallelism over images. Electronic medical records, which actually tend to be actually related to people. Gene sequences, material properties, manufactured object specifications. These are custom data sets running over a particular field. And another example we find is parallelism over things that are being modeled, like vehicles and people. Another area where parallelism is seen is over the members of the Internet of Things, where they're meant to be by 2020. Various estimates, but at least over 50 billion things sitting there. So that's a pretty large number. Another important concept, which has different meanings in different contexts, is events. If you have a telescope recording the cosmos, and then you might look for anomalous events like exploding supernovas represented as changes from in an image from night to night. Another set of things are like fraudulent credit card use or turbulence in the atmosphere. So these are um, the detected outlier, unexpected, um, or specially recorded happenings. And of course, there can be lots of those. Many people think graphs are going to grow in importance because if you set up a chain of consequent chain of connections, say between doctors and hospitals and drug companies and drugs and diseases and patients, that will end up as a complicated graph with complicated interconnections with meaning to the interconnections. Processing such a graph is highly non-trivial. There are other types of networks, or actually also graphs, in fact, which are rather simple. If you take a learning network, as we covered in one of the use cases, those learning networks have huge size, billions of nodes, and those, however, have a simple structure. They're not generally regular structure with the doctor, disease, patient, hospital graph had. Another set of things you get parallelism over is the tweets, and the blogs, and the documents, and the web pages, which you see when you do information retrieval, and you would also get parallelism over the characters and words in those entities. A lot of those applications are set up in the so-called bag of words model, where the words essentially represent the dimensions of vectors representing the document. Another simple thing you have parallelism of is just the resources, like the files or the data itself, when you want to do parallel backup or process the data in some sense in parallel. And several of the applications involve large-scale simulation. When you do large-scale simulation and do parallel computing there, you'll find parallelism over particles, parallelism over cells carved out in the domain you're working in, also parallelism over mesh points. So those are the things you get parallelism of. All of these are things which are large, and it's the bigness of the number of these things which means you get big data. When you look at the runtime or the computational structure of these problems, we introduce the following types of classification. One important class is PP, pleasingly parallel, or sometimes embarrassingly parallel, or sometimes, if you're thinking from a MapReduce point of view, you call this the map-only category. All the entities involved in this type of calculation, although they all come from the same application, they're effectively can be processed independently. That's why it's pleasingly parallel. There are no difficult synchronization problems. Then we have MapReduce, which we'll cover more than once in this class, and it was given in much more detail in the cloud computing class in this data science curriculum. Out of the fifth, so PP, pleasingly parallel, was around 8. MapReduce is 16 of the 51. We could use a MapReduce paradigm. MRStat is a variant of the MapReduce paradigm where the reductions are particularly simple as they're just global sums. 19 of the applications involve so-called iterative MapReduce. They have the map followed by reduce structure, but they don't stop there. They iterate it because the algorithm is not finished after one wave of maps followed by one wave of reducers. Now the graph, which is a data structure, and the things in whose nodes are what we get parallelism over, or the sets of nodes we get parallelism over, they actually need different runtime. Um, there is a famous Apache project called Giraffe, which is a graph processing runtime. Fusion is another important area. So that's just a shorthand for data fusion, which means that you have an application which has lots of different types of data. And to really understand what's going on, you have to combine these different types of data. If you were a commander in a battle, you will be receiving information from your um, weather group about the weather outside. You'll be hearing from all your different spy satellites on eavesdropping communications among the enemy forces, and you'd have local videos recording what was going on the battlefield. So in order to make decisions, you would need to integrate and fuse all that data in a fashion which allows these decisions to be made, or the case of a scientific application discovery to be made. And so fusion is a very important general capability. Something which is important when it's needed, but not always present, is so-called Monte Carlo simulation. The particle physics application is notable that it actually needs as much computing to do so-called Monte Carlo simulations as it does to observe the actual process the actual data itself. So Monte Carlo simulation generates fake data and it's used to essentially debug your entire analysis process and to calculate the reliability of it. You typically need a lot of such events to be able to get a good solid number for the reliability, which will depend on the type of event you're observing. Another hot topic is streaming. Apache has three streaming projects: Storm, S4, and SAMSA. And that means that the data isn't just one giant block of data. It might be that, but there's also streaming, namely data coming in and individual data points which need to be processed. And they're not just accumulated for some giant batch run with all the data. Here is that was sort of the low-level runtime, the nature of the parallelism. At the higher level, we introduced the following types of characterization. Not surprisingly, a lot of the applications involve classifying or characterizing data, dividing into clusters, dividing news into topics, telling the user of an e-commerce site what they really ought to be looking at, so classifying items into interesting and uninteresting. So that's 20 out of the 51. A lot, of course, involves search and query. You have a big data set of diverse types, and then you need to search that data set and according to special user queries. Often that is enhanced by finding indices, because indices are essentially a way of speeding up search. Collaborative filtering is a critical technology used in recommender engines, and we have 4 such use cases. Machine learning, this is an underestimate of the number of machine learning use cases. In a lot of cases, the use case didn't give me enough detail to really pin down the nature of the machine learning, so I left it off. Support vector machines, clustering, those are effectively machine learning algorithms. Latent Dirichlet allocation here is slightly less well-known machine learning approach. In the case of machine learning, we will find there's 2 important differences, different types of use. The simplest, often associated with the pleasingly parallel model, is the machine learning is applied separately to every data point being processed, or every small set of data points data being processed together. So those are called local. Um, they tend not to involve any parallel computing. It's the parallelisms over those points. But if you are doing the machine learning over an individual point, then you're going to be running it on a sequential machine. The other category here is obviously opposite of local is global. That says the machine learning involves simultaneous variation of the features of many of the data points, what here are called items, and that a global consideration needs to be done over everything. Often those generate iterative MapReduce style computations. Machine learning is typically used in classification. That's why I say the 5 is smaller than the 20. That says that there was not enough detail for me to actually find out what was being done. We have this peculiar classification called exascale global optimization, which is a rather whimsical way of referring to large-scale optimizations, often set up as a sum over data taken across the web. And there are various nifty ideas here: variational Bayes method, lifted belief, stochastic gradient descent, multidimensional staining, machine learning. The global machine learning always ends up as sort of ego, because machine learning is always essentially an optimization algorithm. LBFGS is a particular gradient descent algorithm. And all of these are just examples of ego applications. You have giant optimizations done across all possible variables. An important computational type is expectation maximization, and it's often used in machine learning to calculate, especially the global, effectively the global ones, because you'll need an iterative approach to solve it. And expectation maximization is the natural iterative algorithm. GIS is very important. Lots of these big data are associated with space and time, either on Earth or in the cosmos, and that gives you geotag data. And then you use these tools like Google Earth or the Esri, ArcInfo, etc. products to display them. Then we come to high-performance computing. Several of the use cases involve both high-performance computing, producing data, and high-performance computing to produce models which can be compared with data. And then the last class is agent-based computing, where your agents are used when you have trying to produce a model of some sort of large macroscopic entity, such as a person or a vehicle. That's when you say doing a transportation model for a city. And then you would use agent-based computing. Here we have more on the overall kernels. We have, and these actually even list you the use cases. So when it says 1 to 5 across opposite classic database, which gives one example here, the National Archives, it says that use cases 1 through 5 exhibit that. Actually, I think more of them do, but these are just ones I identified. As we'll discuss a little later on, NoSQL is going to be very important, and databases built on NoSQL are growing in importance. So HBase is an important technology here. And then we found media applications, search applications, health applications, artificial intelligence, and network science, all of which wanted to use NoSQL to store their data. And then they would typically, once they're in a NoSQL database, such as Cassandra or MongoDB, it is somewhat easier typically to apply modern data and analytics and machine learning to them. That's because NoSQL tends to distribute the data in an intuitive fashion, consistent with the parallelism of the big data problem across the nodes of the computing system. We also, some applications just process data. They don't even care too much what's in it. If you're adding metadata, that's sort of true. And certainly if you're doing backup, it doesn't really matter what's in the data. It just matters how big it is and where it needs to be backed up. We've already pointed out GIS, Geographical Information Systems. That's needed whenever you see a spatial structure and big data. And anything connected with Earth and physics and engineering, they all tend to be 3 dimensions, and therefore you'll get the GIS being important. We, another class are just built around hosts of sensors, or sensors are again the Internet of Things, and there are, I think, 8 such applications there. Pleasingly Parallel really pointed out how important that was, and that can involve actually quite a lot of computing at each point, like in the CERN analysis and the Large Hadron Collider. It takes 10 to 20 seconds to analyze each event. After that, we mention high performance computing assimilated with observational data. And simulation is a way of using the data to improve the simulation. Because inevitably, when you are doing weather simulations, for example, you don't have enough data to be precise. We already pointed out why agents were important, and also why we need to do data fusion, which is sometimes called knowledge management. These are rather wishy-washy, undefined things because they're built at the high level on top of the core analytics. And then finally, we pointed out that crowdsourcing is a key algorithm in some cases. That's where you harness the power of the people to do the analysis. After that, we can give some details of the machine learning used. But most of the use cases, actually, not just some, but most really don't give you enough detail to pinpoint the analytics. There are algorithms like latent dimension allocation, which are used for classifying documents in an unbiased fashion. There are many such algorithms. There's 4 cases here of that. We mentioned ego, large-scale optimization as an important class. Recommender systems were started off in information retrieval, but sorry, in e-commerce and places like that. They are now becoming built into lots of different applications. Learning neural networks are a particular way of optimizing automatically from big data. Graph algorithms are often, as we'll see, the most efficient way of solving problems. When we come to machine learning, let's look at the global ones. Those are the big problems. And then you can see at least 2 different classes. One, like support vector machine, have a computational complexity of order the number of points in the data set, whereas something like multidimensional scaling goes like the square of the number of points in the data set.